So today we're going to be talking about 4 really cool ideas. Some of these are going to show up again and again as we go through. Some of them are going to be lurking in the background and we don't need to worry too much, but we need to say things at some point. So let's begin. Our first idea is the idea of how do you verify a solution? You see, we have a differential equation. So in other words, some equation that involves derivatives. And the goal of our class is ideally to solve it. Now, finding solutions is hard. But verifying solutions, that's not so bad. Because what does it mean? Well, it says you take what you think is the answer, in other words, it gave you something, and you plug it in. And you plug it in. Does it work? If it does, you've verified. And if it doesn't work, it's not verified. Now, the nice thing about a problem that says verify something as a solution is you know it's going to work. And so if it doesn't work, well, okay, you made an algebra mistake somewhere or took a derivative wrong. All right, so just step back and check your work. Now, this idea of verifying, we may not use very often, but the principle, there's this beautiful thing that says, hey, plug something in and look at what happens. And that idea shows up a lot. So in other words, we plug something in that we think is close to the answer. Maybe there's some little knobs or something to turn and levers to pull, but we have to find just the right settings. And so this gets us to this idea of saying, hey, plug in something, see what happens. Now, on a philosophical note, there's a few ways you can approach problem solving. And, one way you can look at it is you say, look, I've got my problem here, and we try something, right? Because, well, you should always try something. You should never say, I've tried nothing, and I'm all out of ideas. You should always try something. Now, the really cool thing, of course, is if we're correct, and then what happens? Well, we're happy. And we think to ourselves, aha, we have become calculus, the solver of problems. And, we're just stoked. Now, the other thing that might happen, hopefully, it doesn't happen very often, but, it might, is we get it wrong. And what happens? Well, oftentimes what happens is people are sad, and then they sort of spiral and just give up. And if they spiral too far down, they may end up becoming underwater basket weaving majors. We don't want that. So I want to talk about sort of a different mindset that you should have that comes back to this idea of plug something in and play around with it. Because it's actually a really good mindset to have in problem solving. Namely, yeah, you have your problem, and as before, sure, it's nice if you get it correct, and because, yeah, we're happy, we got the answer. Okay, so no big surprises. But here's the thing. If you get something wrong, don't feel bad. You can be like, meh. You don't have to be excited you got it wrong, but don't feel bad you got it wrong. Because oftentimes, getting something wrong, you'll learn something. Mistakes are incredibly useful and incredibly valuable. Some of the most important scientific discoveries and mathematical discoveries came from people making mistakes and saying, well, that's weird. Why did that happen? So what do? Well, you don't spiral down. You say, okay, let me take what I've gone here and let me learn from it and let me plug it back in. So, in other words, refine the guess. And that's oftentimes how solving problems work. You try something, and if it doesn't work, look at what happened. And then use that to try something else. But never give up. Good pieces of advice. So let's try one of these verify problems. So verify that y equals tangent of x is a solution to this differential equation. Now, it's a differential equation. It's an equation because we have our equal sign. And it's a differential equation because there's derivatives involved. In fact, there's a first derivative and a second derivative. Now, how do we proceed when we do a verify? Well, the answer is everywhere that we see a y, and we see it here in 3 places, the y prime, the y double prime, we're going to put in tangent of x. And of course, since we have derivatives, we'll put in the appropriate derivatives as we do so. So let's first start by taking some derivatives. So we know that y is equal to tangent of x. The derivative of tangent, well, we can figure that out. We can even look at the formula sheet if we needed to. It's secant squared. Okay, no big surprise. Y double prime. Well, if I think of secant squared, that really says the secant function squared. Well, the 2 comes down, so then that becomes 2 times secant of x to the 1 times the derivative of secant, and the derivative of secant is secant tangent. Or we can write this as 2 secant squared x tangent of x. All right, so now we have our y prime, and our y double prime. So what's going to happen is we're going to plug these in to the right places and see what happens. So ideally, if it is a solution, and we know it's going to be, when we plug it in and simplify, we should get 0. All right, so here we go. We have x minus sine x cosine of x times y double prime to secant squared x tangent x minus 2x tangent of x times y prime, which is secant squared x, and then plus 2 tangent of x times y, which is tangent of x. Okay, so there we go. We've plugged in. So in other words, let's make a little note here. We have the following. This part is our y double prime. Here is our y prime. And here is our y. All right, good. Now we simplify. It's going to be a little bit of algebra. We see trig functions, a little bit of trig, but you know, we're just patient. So here we'll distribute. So we have x times that. Okay, no worries. That would make that 2x secant squared x tangent x. And then we have the minus. All right, careful with your signs. Minus signs are one of the most common things to make mistakes with, so we'll be careful. All right, so now what do we have? Well, we have, well, we'll go ahead and write down the whole thing. A sine x cosine x, and then a 2 secant squared x tangent x. I suspect this is going to need some work, but that's all right. We'll get to it. Now here, we have minus 2x tangent x secant squared x, all right, and 2 tangent squared x. Okay, well, one part is not so bad. Namely, the 2x tangent x secant squared x. Pow, pow. You don't have to say pow, pow, but sometimes it's not, you know, you can do it mentally. All right. What about the rest? Well, let's focus our energy here. And oftentimes, sort of the mindset is the humans were made to simplify things. So if you have a choice between working with something that looks complicated or something that looks simple, say, let me take the complicated thing and try to make it look like the simple thing. Because that's what we're built for. We're not built to make things more complicated. Or maybe you should say, you know, the real challenge is there's too many ways to make things complicated, whereas when it comes to simplifying, there's sort of fewer. Well, what can we do? We have cosine and secant. Now, secant is 1 over cosine. So when you multiply a cosine times a secant, whoosh, it becomes a 1. So we can say, oh, if I cancel a cosine and a secant, that's good. All right, well, that's simplified. What else do we have? Well, the tangent is good because that's the tangent. Sine times secant. Well, that's sine times 1 over cosine. Or sine over cosine, which means that when you put these together, this becomes tangent. So what do we really have here? Well, we have a minus, a tangent x, a 2, and a tangent x. So that's minus 2 tangent squared x, and a plus 2 tangent squared x. And we say, aha, nice. That is really in good shape for us to cancel. And so we go, pow. They're canceled out, and we end up with 0. Whereas, what did we want to end up with? 0. So, kapla, which of course means Klingon for success. And so, what do we say? Well, it's verified. And, well, I usually like to put, I'm happy. All right, so good. That's the verification. That's an example of what to do. Now, to see an example of how we use verifying to find solutions, let's look at this one. Find a solution in the form y equals e to the power b times x for the differential equation y double prime minus 8y prime plus 12y equals 0. So notice it doesn't say y equals e to the bx is a solution. It says, well, some choice of b might be a solution. So our goal is to say, well, maybe, 17. Who knows? Well, we will soon, right? So what do? Well, we run through the same process, plug it in, and we see what happens. So we say, well, we start with e to the bx, and we're going to have, again, we have our y prime, y double prime. So we'll take our function and find our derivatives. And when we do that, we get e to the bx, b times e to the bx, and b squared e to the bx. Plug it in. So y double prime minus 8y prime plus 12y would become, well, y double prime b squared e to the bx minus 8y prime b e to the bx, and then plus 12y. So plus 12 e to the bx. You might notice, by the way, I'm being very generous with parentheses. Partially because, parentheses are free to use, so we can be very generous. But also, it's a good habit to use parentheses because it really makes sure we don't lose any distribution. Now here, it doesn't really make much difference, but there are times when it does, so it's good. Be generous with your parentheses. Save points. You want to save all your points. Now we start saying, okay, well, let's clean this up a little bit. Notice they all have e to the bx in common on each term. So we can go ahead and pull that out. Pulling it to the front, we have e to the bx times b squared minus 8b plus 12. Progress. This feels like a polynomial. And it feels like it's a polynomial because it's a polynomial. Yeah, see, there's a good reason why it feels that way. We say, well, we have ways to deal with polynomials. For example, we can factor. At least we can try. We're looking for two numbers that would multiply to 12, but add to -8. Well, it doesn't take too long to think of numbers that do that. They're both negative. Okay. 3 times 4, no. 1 times 12, no. 2 times 6, oh, yeah. 2 times 6 is 12, and minus 2 minus 6 is 8. So I say, okay, so this is e to the bx times b minus 2 times b minus 6. Now remember, we want a solution to this differential equation, which means that all of this has to equal 0. Okay, so now at this point we start looking. We have 3 pieces here. Well, we say, can e to the bx be 0? No, Never, never. It can never be 0. Could b minus 2 be 0? Well, yeah, it could be if b were equal to 2. Could b minus 6 be 0? Yeah, it could be. That would be if b equals 6. Now, notice we're at the stage where we have several things multiplying together and we get equals 0. There's this cool fact about 0, and that is if you have a bunch of stuff multiplying and you get 0 out, something had to be 0. So that's why we can really split it up and ask, well, what happens to make that 0? What happens to make that 0? And so we say, oh, okay, so there are choices for b which will always force it to be 0. So in this case, we actually have 2 choices. So it asks for a solution, but we can say, hey, we can do better than that. We can give you 2 solutions. So, namely, you can have y equals e to the 2x. This is if b equals 2. Or y is equal to e to the 6x. And this is if b equals 6. So either one of these will be a solution. We know it will be because we could just run through the verification. And because of the way we've chosen our b, we know automatically it's going to work. So we're going to do this, by the way, a lot. And so this particular idea of saying, oh, e to the something x, let's try it out, let's see what happens, that's going to happen a lot. And so this is a shadow of things to come. So this brings us to our second thing we want to talk about, which is what we call initial value problems. And that is when we have an initial value. So in other words, what we have is we have our differential equation, and when we solve it, think about Calc 1. When you solved a derivative, you integrated, you had a constant. And you said, well, what's the constant? You need some initial value. It's the same thing here. When we solve a differential equation, it's essentially doing an antiderivative in some way, shape, or form. And when you do that, you introduce one, possibly several constants. It depends on how many derivatives are involved. And then you say, okay, what information do we have? And do we have that enough to help us figure out the solution? In other words, the solution that satisfies all the constraints. And I will say there's a little piece of advice that says, in terms of how many initial conditions you have, look for the order of the highest derivative. So when we talk about order of differential equations, you say, what's the biggest derivative involved? So if the biggest derivative is the second derivative, we call it a second order. And then in that case, you want 2 initial conditions. If the biggest derivative is a first derivative, we call it a first order. You need 1 initial condition. Okay, so we have a simple example, and we'll just do a simple one for now, but we will do initial conditions a lot. So just a word of warning, you'll see this again and again and again. So this should not surprise you at all. Essentially, it's a solve for c that we've seen before. All right, so our example. Verify that the function log of x plus c, where the plus c is inside the log, is a solution to e to the y prime equals 1. Find the particular solution if the function also satisfies y of 0 equals 1. Now, a couple of things. First off, notice how the plus c is not on the end. See, when we were taking calculus, we're so used to saying the plus c, as always, don't forget that at the very end. The constant can be in different places now. Maybe it's multiplying in the front, maybe it's on the inside. It can move around. So don't always think, oh, it's going to be a plus c on the end. That's not the case there anymore. The other thing that's going on here is what we have is to say, this isn't really one function, but infinitely many. It's a family of functions. Each choice of c gives us a different function, all closely related one to another, but again, a slightly different one from another. And so what we're saying is, out of this whole infinite family of functions, find the one that has that special property, And in our case, that special property is that y of 0 is 1. Okay, so first off, the verify. Okay, so what do? Well, we just want to plug it in. So we say, all right, well, that's e to the y prime. Well, e to the natural log of x plus c, because that's what y is. Now, the derivative of natural log would be 1 over the inside times the derivative of the inside. And the derivative of x plus c would be 1. Now, e to the natural log, they undo each other. And so this becomes x plus c times 1 over x plus c. And then we're like, aha, which is 1, which is what we want. E to the y prime equals 1. And therefore, we have verified. Good. We are happy with that result. Okay. Now to the next part, which is the particular solution. All right. So now what do? Well, we have to find c. So we have this y of 0 equals 1. Now, the notation here, that y of 0, that's acting as our input. So that really says x equals 0, y equals 1. So that's what that means. So you plug in x equals 0, plug in y equals 1 into your solution, and then say, okay, what needs to be true? So let's do that. So we have that 1 needs to equal natural log of 0 plus c. Okay, so now the question is, what's the right value for c where this is true? Okay, log of what is 1? Well, if you know properties of logs, you might be saying, aha, I know it. And if you don't, you might be saying, aha, I can figure it out. So the easy way to figure it out is say, well, let's just get the c outside of the log. And the way we do that is exponential functions. So we can say c is e to the natural log of c, right? Because e and log undo each other. But I know natural log of c is 1, so that's e to the 1, also called e. All right, now, is this our answer, and why not? You're right, it's not our answer, because what are we after? It's one of those things that when you're doing a problem, you always want to make sure you know what your final answer should look like. You know, what is it that it's asking us to find? Well, it's after the particular solution, and what we've identified is the right constant for the solution. So what we need to do is just put the constant in. So to finish, we put in c equals e. So we get that y is equal to the natural log of x plus e. And that is our answer. All right, there we go. Like I said, we're going to do this a lot. There's no big surprises. You find your solution, and we're going to be talking about ways to do that. Solve for c. Now, there's one small thing I will say is you might start asking the question, when do I solve for c? And we will see examples of this as we go on. So I'm just going to tell you a good rule of thumb right now. Solve for your constants when it's convenient. So if there is a time when you say, oh, it would be really convenient to solve for my constant right now, go ahead at that stage and solve. And if it's not convenient, yeah, you can wait and do it later. And we'll see examples of that as we go on. All right, on to our next topic. So the third thing that we want to be talking about today is this notion of word problems. We're not going to dwell on it very much because in some sense it's not a high priority. We're going to do a little bit of practice here and there, but we're going to keep it relatively simple. Now, this is a non-trivial skill set. It's the taking of English into math. You know, and that's not the easiest thing to do. And the way you do it, of course, is practice, but you look for key parts. You know, you look for numbers because oftentimes they show up in formulas. You start saying, do they give you any variable names? So they might say, oh, the population P. It's like, okay, cool. Well, P is part of my equation. Start looking for things which vary. So if things are varying, those are variables. Those will probably show up in our differential equations. Start looking for keywords. Look for things like rate or change. That's where you'll see derivatives show up. If you ever see the word is, that's just another way of saying equals. If you see that word proportional to, that means things like there's a constant scaling factor. All sorts of places where words show up. When you think about, just sort of start parsing the sentence and saying, okay, how does this translate into an equation, a formula that we can use? So let's do a couple examples. So here's our first example. Set up a differential equation for the curve y equals f of x, which satisfies that the tangent line to the curve at a point x comma y hits the axis at the point 3x comma 0. Now there's a second part which says, what if instead of the tangent line, we use the normal line? And we'll talk about that one after we finish the first one. Okay, so first off, when in doubt, if you can, draw a picture. So there's a point, xy. And what is that? Well, so we're in the plane because it's an x comma y. Okay, here's x, y. And then it says that our tangent line hits the axis at the point 3x comma 0. Okay, so if there's x, 3x, well, that's going to be over here. It's going to hit roughly right there. And say, all right, good. Now, what do we have? Well, we have our tangent line. Cool. So this is our tangent line. So far, so good. But now you start saying, but wait, where does the differential equation come into play at all? Well, okay, so we know a differential equation means there has to be a derivative involved. So we start thinking about derivatives. And we say, well, our problem involves a tangent line because it's right there. Is there any relationship between tangent line and derivative? Slopes, right? The slope of the tangent line is the derivative of the function. So our great aha, light bulb turns on, is, oh, okay, so let's think of the slope. We say the slope, well, it could be one of two things. It could be y prime, so the slope of our tangent line, or it could be what this slope is. And notice we have 2 points. And the nice thing about 2 points is 2 points determine a line. So we say, oh, okay, well, a slope is the change in the y. So I could take the difference, y subtract 0, over the change in the x. So, okay, so that would be x subtract 3x. So just make sure you're consistent. And, okay, so that's, there's a y upstairs, a minus 2x downstairs, so that's minus y over 2x. And what do you have? You have a differential equation. Y prime equals minus y over 2x. So for our tangent, we get y prime equals minus y over 2x. Good. We're done with the first part. Okay, now you might say, well, that seemed too quick, too easy. And what was the key? Well, the key was to think about what we had, namely a tangent line, and how we could relate it to a derivative, namely the slope. And once we have those two ideas, everything else falls into place. All right, now there's a second part that says, what if instead of the tangent line, we used the normal line? Now, what's the normal line? Well, you might remember normal as normal vector to a plane, and the normal vector to a plane was one that's perpendicular to the plane. So the normal line is the line That's perpendicular. So this is our normal line. So we say, okay, so the normal line is perpendicular to the tangent line. Well, when are two lines perpendicular? You remember? A little bit of algebra, I know, but just a little bit. The slopes are negative reciprocals. So you have to change the sign and you have to flip it. So, say, okay, we need the slope is the negative reciprocal. So we have the negative of negative, so the negative goes away. Reciprocal means flip it over, and we're done. That's it. So once you understand things, it's not so bad. You know, when you originally look at something like this, you're like, whoa, this looks scary. But then you look at the solution like, well, that's not so bad at all. Because it's not. But it does take practice, and we will get some. Because we will see examples of problems. And, you know, it's coming. Good days. Here's another example. On their 30th birthday, an art history major opened an IRA account. So, you know, this is a very optimistic art history major. They think they're going to retire. And the account has a return of 5% and starts depositing $500 each year. So part of it, what's going on is that, you know, every year they put in $500, but you know, that's, you know, art history, you know, you get what you get. So that's one way that the IRA grows. So IRA is individual retirement account. So what's happening? So there's money coming in, but then there's also this sort of internal growth. So a return of 5% means that every year, if you did nothing, it would grow by 5%. Now there's a nice word here to point out, which is the word and. When you see the word and, what that means is oftentimes that there's multiple effects, and usually when you see the word and, you should think about a plus. Now that's not always the case, but oftentimes you should think of it as somehow there's multiple things going on. So in our case we say, okay, two things are causing growth. Now what do we need to do? We need to set up an initial value differential equation for m, and m is the amount in dollars in the account at time t in years since turning 30. All right, so initial value says, okay, we need to say what's happening at some time. Usually it's time 0, doesn't have to be, but usually it is. And then the differential equation says, okay, how is it changing? So we say, all right, well, we can figure this out. What do we have? We have m prime. That's how the money is changing. And we know there are two effects. We need to add them together. Now the two effects are, there's the deposit made each year. That's one way that this money grows. And the other one is that 5% return. Now, the nice thing about the deposit each year is it's fixed. It's $500 each year. So we say, okay, so that's plus 500. What about the 5% return? Well, the 5% return says that, you know, imagine you have $100. Well, 5% would be $5. So that says you get $5 extra. So the 5% return, well, you say, okay, 5%, that's the same as 1/20th, right? Because 5% is 0.05, which is 1/20th, times the current amount. So if you had $100, that would translate into 5. If you had $1 million, that would translate into, well, more than $5, 50,000, I think. And so, okay, so it just depends. The larger m is, the more money you get. The smaller m is, the less money you get. And by the way, this is one of those beautiful things about compound interest. You know, it doesn't feel like a lot's happening at the start, but over time it grows, and in the long run, it gets pretty big. And Okay, are we done? We've set up a differential equation, so that we must be done, right? Well, we're missing something. We're missing the initial value. Okay, so how do we do that? Well, we just say, what's the problem tell us? On their 30th birthday, they opened the account. Great. So how much money is in it when you open an account? Well, nothing. You know, they're not going to give you an account and say, oh, here's a lot of money. So at time 0, where we say there's nothing in there. Now you might say, well, wait, didn't they put $500 in initially? Well, okay, so this is one of the things about mathematical modeling. We just say, look, let's just, this is not the conversation I wanted to have. You've put me in a corner. So in some sense, there's the notion of continuous versus discrete. In this underlying model, we sort of say when we put $500 in each year, it's kind of like we put $500 spread out evenly throughout the whole year and not necessarily as one big chunk. You might say, well, doesn't that change it slightly? It does, but in the long run, you'll see that the continuous versus discrete is not really a significant difference. And oftentimes we find it's very convenient to assume that it's nice and continuous as we do our modeling. All right, so there we go, our differential equation with our initial value. And we've set it up. Life is good. Can we solve it? We will. At least solve problems like this. Just wait a few more days. So this brings us to our fourth and our final thing that we want to talk about. And this one is one that we're not going to dwell on very much, and we may not even mention it again explicitly. But it's one where mathematicians care about. And that is to say, do our solutions make sense? In other words, there are cases where we have a differential equation and some initial conditions where there's no solution at all. And there are also cases where we might have infinitely many solutions. We're going after that sweet spot. One solution. One solution to rule them all. One solution to find them. One solution to bring them all, and in the light of differential equations, bind them. So we want the one solution. Now the good news is that for most of the problems that we're going to do, in fact, for the vast majority of problems that we're going to do this semester, we do have that situation where there's one and only one solution, at least over some defined window. And when can things break down? Well, essentially, two things might happen. And as long as we avoid those two things, life is good. The first thing that can happen is that the function itself breaks down. And by this, I mean things like it might blow up asymptotically. There might be some weird thing going on. Now, why is that important? Well, in essence, when the function breaks down, what it's saying is we don't know where we are. So we need to know where we are. That's always important. And so if we have an asymptote, well, we can't know where we are. And so that's why it's bad when our function breaks down. The other thing that can happen is that the differential equation itself breaks down. Now, if we think of our differential equation as y prime is a function of f of xy, what we're really saying is, look, we don't want f of xy to somehow have a problem, maybe like a 0 over 0 or some sort of weird discontinuities. So why is that important? Well, that's important because we need to know how we change. So the philosophy of differential equations can really be said when we have an initial value problem for a differential equation, we start where the initial value says, and then the differential equation says, how do you move? And so you just start, move, start, move, start, move. So as long as you know where you are, and as long as you know how to change, you should be able to move along in a unique way. So when things break down, one of these two things had to break down. Either you didn't know where you were, or you didn't know how to change. And that's the underlying philosophy. And so when you understand that, it's like, oh, That makes sense. Okay, so as long as I know where I am, as long as I know, it makes sense to say what the change is, life is good. And so that's why we're going to avoid this discussion for the most part. We might see one or two pathological examples just to sort of whet our appetite. But the nice thing is, keep in mind, what we're doing this semester is actually useful. That's the important thing. We really are doing useful stuff. So one quick example to illustrate what we just talked about. So verify that this function y equals 1 over c minus x is a solution to the differential equation y prime equals y squared. Okay, so before we read any further, let's just quickly take care of that. So we have that y is 1 over c minus x. Now notice we could have written this as c minus x to the power negative 1. So how do you take that derivative? Well, do a chain rule. So first off, to the outside, the negative 1 comes down. Then you have the function, the inside stays the same. Subtract 1, so that makes a negative 2, times the derivative of the inside, which is negative 1 again. Negative 1 times negative 1, okay, those cancel out. So we really have c minus x to the power negative 2. But we say, well, this is c minus x to the power negative 1. To get to c minus x to the power negative 2, you square it. So that's y squared. And that's our verify. All right, good. We've now verified our solution. So we have, again, many, many solutions. Every choice of C is a valid solution. Okay, so next sentence. Find the particular solution which also satisfies y of 3 equals 2. All right, well, great. So in other words, hey, here's an initial value. So what do? Well, y of 3 equals 2. Again, as we read this 3 here is the x value, this 2 here is the y value. And so we say, well, we need to have that 2 is equal to 1 over c minus 3. All right, well, that's not so bad. We just need to solve for c. Well, let's flip both sides. And if we do that, that says, oh, c minus 3 is 1 over 2. And then we can add 3. So c is 3 plus a half, which we can call it 3.5, or we could also call it 7/2, whichever one you like to do. I'm more of a fraction kind of guy. Engineers would be more of a 3.5. Well, actually, an engineer would probably be more of a 3.5000, because, of course, 4 digits of accuracy makes it even better. Okay, but the point is we know what C is. Now that we know C, we can plug it in, and we say, lo and behold, our particular solution looks like 1 over 7/2 minus x, and good. Now, what can we conclude about y of 5? Given the discussion we just had, we would probably be like, if we hadn't just finished our discussion, what's your instinct say to do? Instinct says plug in 5, right? Cool. So if you plugged in 5, all right, let's do that. Then we say, okay, so y of 5 is equal to 1 over 7/2 minus 5. Okay, 7/2 minus 5, that's 7 over 2 minus 10 over 2. So this would be the same as 1. And then a minus 3 over 2, or negative 2/3. And you look at this and say, all right, sure, whatever. There you go, Steve. We got the answer. Well, that must be it, right? 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 Okay. All right. Now, there was a reason, of course, we're doing this now, because this is actually not the answer. All right, so let's take a look at our function. All right, so here we go. Now, we'll plot. We have y equals 1 over 7/2 minus x. Our initial value is at 3, 2. And so what we can do is we say, okay, let's plot this. Now, 1 over 7 halves minus x has an asymptote at 3.5. So this is at 7 halves. And when you plot in that curve, what we see is the following. And let me grab a good color here. We get something that looks like that. Now, the question is, what's over here? And they might say, like, well, can't we just do that? Well, the problem is we don't know. This asymptote breaks it. So the right-hand side, we have no idea what's going on here because we cannot move past it. Remember, we're starting here and we're moving because the initial condition tells us where we start, the differential equation tells us how to move, but I can't get past the asymptote. I can't even get on the asymptote, so I can't move over to here. So the correct answer is not negative 2/3. The correct answer is that there's no conclusion. We can only go up to the asymptote, but we cannot go past it. Now, on the other hand, we can keep going all the way to minus infinity because there's no problems. There's no asymptotes. And if you look at our function, y prime equals y squared is a beautiful function. Beautiful function. It's the kind of function that we wouldn't mind taking home to meet our family. So this is an example of how things can go wrong. There are, of course, other examples. We're not going to stress about them. They won't show up too often, and when we do, we'll point them out. All right, so that was it. 4 good lessons for today. We talked about, how do you test whether solutions are valid? Spoiler alert, you plug them in. How do you work with initial conditions? And answers, solve for C. And solve for C when it's convenient. What do you do for setting up a differential equation? Well, you start reading sentences and you start sort of breaking it apart. Words mean something. Translate the words into what they mean. And then the last thing, of course, is when do solutions exist and are they unique? And the answer is when we know where to start and we know how to move, life is good. Okay, so that's it. And next time we're going to start getting into first order differential equations and learning how to solve them. All right, well, have a good day.